Hello everyone, and welcome in another episode of the JAX for Deep Learning series. Today, inshallah, we will go through the JAX transformation functions and a small overview about the JAX ecosystem. So you are always with Leila Habib, GDG Sidi Abbas, organizer and the WTM ambassador. So for those who didn't attend last session, we talked in general about JAX. We said that JAX is a powerful and a flexible ecosystem for machine learning research. It's built on top Python and NumPy, so it's provide an extensive set of tools and libraries for developing, training, and doing a lot of stuff. Okay, so especially in machine learning, so training some machine learning model, including the deep neural network, of course. So with a focus on the performance and scalability and the ease to use. Okay, so this is the reason why they invented JAX, okay, especially for the performance and scalability. So the JAX ecosystem here offer a lot of libraries and tools, including HiQ and Optax that we will talk about in this session, inshallah, and in the next session. So as I said, the some tools, there are some several tools that are built on top of JAX that help, or let's say they are, or let's say if they enable developers and researchers to quick and easy build and train and optimize some deep learning models. Okay, and additionally, JAX provide a suite of APIs of high performance computations, especially on CPUs and or let's say GPUs and TPUs, as well as for the distributed training, allowing researchers to train and test models at scale. Okay, today inshallah we will just like say we'll just like go deeper in this topic, where we'll talk about the JAX transformations functions and JAX ecosystem. Okay, so as we mentioned that JAX is built on top of NumPy library, and it's compatible with the most exacting let's say most existing Python code, and it's also provide a number of advanced features such as the support vectors operations. So those transformation, those features, or let's say those features, yes, we can include them, or we can add them in those transformation functions. Okay, we can list them as transformation functions. Okay, so let's start. JAX for function transformation. So JAX, here we have about 4 commonly used functions for transformation that can be used to modify and give function a various, let's say, we can let's say modify things and transform data, transform information that we're having in a different way, in a various way. Okay, starting with the two first function, let's say it's a JAD grade. So this function here is also a transformation function. It's used mainly to compute the gradient. Okay, so it's compute the gradient for a specific function or for a given function. So it takes a function as an input and return a new function that compute the gradient for the original function. Okay, I don't know if you got what I mean, but it just like we're having a function, thanks to this JAX grade, it just like help us to have the gradient of a specific function. So this can be used for automatic differentiation, which is, let's say, a key technique to use in deep learning and for training models in general. So here we're having this snippet of code of a simple example to how to use or to how to call this gradient function. First of all, we import the needed libraries. We have the JAX. We can import the grad library from JAX. Okay, so JAX, we can consider it as a framework. Okay, it's a big library or framework, and it contains some modules such as the grad. So grad is also a library that is in JAX. And of course, we could use the NumPy of JAX, because JAX have a specific module called NumPy, has the same functionalities as the alt NumPy that we used to use in Python or in our deep learning process. Okay, so just like the simple NumPy that we know, but it's under JAX, so it will be more efficient and easy to use. Fine. So here we're using the JAX NumPy as GMP. First thing, we're trying to define a function. So this tan age function is defined using JAX NumPy for JAX. and this expo function. We've given it a specific formula here. Okay, and then this function here return the if you can say the hyperbolic tangent for an input x. Okay, so if you just like give a look to this formula here, we're having 1 minus y divided by 1 plus 1. So this is the hyperbolic tangent for a specific value here. Fine. The next thing is the grad function. Okay, here we will be using this grad function. Okay, so the grad function here is it's from JAX, of course, and it's used to obtain the gradient for this tangent function, tangent hyperbolic function. Fine. So the grad function here, it takes this function as an input, and it returns a new function. Okay, it's returning a new function that's taking the first function. Okay, just like please follow with me, just like carefully. We're having our first function here. So let's say this is the function that we're having, and we want to calculate the gradient for it. So we give this function, this specific function, to this JAX function called grad to calculate the gradient. So this grad tangent here, it can calculate the gradient for this specific function. And then thanks to this gradient function, we can just like give a specific point x, and it may calculate the gradient for this x. Okay, if I may give you another example which is more easier. For example, here our function is 2x. Okay, so the gradient of 2x will be 2. So grad for 2 will be 2. Let's say at a point 4 or 5, the gradient for 5 is just like always 2 here. Okay, so this is in general about the gradient. Just like calculate the gradient for a specific points. Fine. So this code here just like demonstrates how easy, let's say, or how easy to compute the gradient here using this grad JAX function by simply defining the original function and using the grad function here to obtain the gradient, and it can compute the gradient for or a specific function at a specific point. Okay, so here x it's 1. Okay, so we replaced x with 1 because we should calculate the gradient at a specific point or with a specific x. Fine, so this is about our first transformation function. As we said, we have 4. So this is for the gradient. Just let me check if there is any question there. Okay, no question so far. Good. Moving now to the second function, transformation function, okay, which is the just-in-time. We talked about it a little bit in the last session. So this just-in-time GTR or just-in-time function, it's used to compile, let's say, it's used to compile a specific function, to compile a given function. When the function is just-in-time compiled here, it can be executed much more efficiently as JAX is able to obtain computational graph of function and execute it in, let's say, using the available hardware resources. So generally, just-in-time function here just like try to accelerate the results. Okay, just like it's help us to get, let's say, to do things in more accelerated things, especially in terms of timing. So it's saving time there by using the just-in-time compiler. Okay, if you want to know more about the just-in-time, please don't hesitate to watch the last episode. We talk deeper about just-in-time and how it's helping to do those, let's say, to accelerate the execution there. Okay, this code here demonstrates the benefit of using just-in-time or the JAX GTR compilation to provide the performance for specific function. So let's define the first function called slow f. Okay, just like here we already know that compiling or executing a function without just-in-time, it will be more slower than with the just-in-time compiler. Okay, that's why we call it slow f, but you can use any other function here. Okay, so any function that you executed simply, it will be more slower than the other one. So this slow f function, it takes as parameter x, and it returns this specific form here. Okay, we're having x multiplied by x plus x and multiplied by 2. So this is, we give it an x, and this is the output. And then to define this x here, we're just like trying to use the JAX for NumPy, okay, Okay, it's not imported, it's here. So we're using the JAX for NumPy function here, and it will, how you say, we're just like trying to create a matrix or an array that contain about 5,000 rows and 5,000 in one. Those arrays is ones arrays. Okay, we just like to replace this x here because this slow function need the x, or need an array as an input, need an input. Okay, so this is our x, and then we are defining a new function. So what's this new function is doing there? So just like this slow function that we're having, but we apply on it the JIT or just-in-time compilation. Okay, we will compile this slow function using just-in-time compiler. Fine. And now finally here we're having this time et here. This comment, it's used for to let's say to calculate the execution time. Okay, to time the execution for both the fast x and slow x. So remember, fast x here, fast f is using the just-in-time compiler, and meanwhile the slow f it's not using any just-in-time compiler. Okay, so just like the function as we wrote it exactly. So the output there for the fast f here is executed, sorry, using this just-in-time compiler, and it takes about 4.5 milliseconds per loop. Okay, and meanwhile the other function it's executed in 14.5 millisecond per loops, which significantly much slower than the fast f function. Okay, it's really clear that while using the just-in-time compiler, we're taking less time. Okay, while talking about the milliseconds, maybe they may look small amount, a very small amount, because it's not even 1 second. Okay, it's a very, very small number here. But yeah, just like imagine we're having a large data. Imagine we're having a very big data. Even though here this array here is just like about 5,000 by 5,000. It's a little bit a big data, but while using the just-in-time compiler, it takes like about a small time to execute for each loop there. Okay. So this, to sum up, this code here demonstrates how JAX, JIT, or just-in-time compiler can be used to improve the performance of a function in JAX, particularly for the large arrays, okay, by simply applying this just-in-time function here for any specific function, okay? So this is just like an example with using slow function. Maybe you're using it for any other function, just like by calling the just-in-time compiler there, so we will have a faster or very efficient result, okay? So we can obtain a compiled version that's run much faster than the original function of any function that you want. Okay, you're not necessary to use it on a function that looks like that, but any function you may execute it using this just-in-time compiler. Okay, and of course, if you want to know more about the just-in-time compiler, as I mentioned, we had a session to talk about the JAX basic, and we explained much deeper about this JS compiler. Okay. So I think here by mistake I just like forgot to write one here, but here basically it's 3, not 1. And now moving to the Vmap, JAX Vmap. So it's also transformation function that it's used to apply as a given, let's say to apply for a specific function to multiple inputs. Okay, so with some computational performance, let's say this Vmap. Well, since we're having a map here, we can use this parallelized operation on a large data sets. Fine. So the overall of this code here, just like demonstrate how we can use this Vmap function in very efficient way that apply on specific function to batch off an inputs. Okay, by batching the input, and JAX can take the advantage of a parallelized hardware to compute the function much faster than the function were applied in each input individually. Okay, so this is particularly useful for neural network, especially because here we're talking about things that may help JAX to do some neural network, because we thought that yes, we may use the we may use the those functions here in neural network, but so far as we don't know yet how to build a neural network using JAX. Okay, so before building this neural network with JAX, we need to know or to get an information about what function the JAX need to do those things. Okay, so we often want to apply some function to multiple inputs in simultaneously, let's say, during training any machine learning model. Okay, fine. So this Vmap here function stands for the vectorizing map. Okay, so this V here for vectorizing and map it's as it is. And here, just like we apply it on this specific function here, let's say the predict function here is a function that we want to apply the batch of an input. So the first argument that we're having here is the parameters. Okay, let's say those are the parameters or my model parameters, and the second argument is the input batch. Fine, for this specific function. And then again, we can see here we were using this in-axis argument that tells the Vmap or inform the Vmap which argument of predict are batched. Okay, so here we're talking about batches. So just like by specifying this in-axis none and zero, it just like help the Vmap to know which is the batches argument. Okay, so here it's clear that we're using none. I mean, the first parameter, it's not batched. Okay, so we're having none here. I mean, the model parameters are not batched. In meanwhile, here the second argument, the input batch is here, is batched along with the first dimension. Okay, so the resulting function by this Vmap function, it takes those two parameters here and try to return, let's say, it output a function which is a batch of predictions. Fine, because here we're using the prediction function. And yeah, this is about the Vmap function. Just let me check if any questions so far. If there are any questions. Okay, fine. Now let's move to another function, which is the Pmap. Okay, we have a Vmap, a Pmap. Fine, so this function is similar to JAX Vmap, but it's used to parallelize operation across multiple devices. Okay, such as when we're having GPUs or TPUs, a lot of devices, a lot of GPUs and TPUs. So this can be useful for scaling up the computation of large models and data set to multiple devices for faster computations. Okay, so we're having this code here. When we talk before jumping into the code, when we talk about the parallel hardware, sorry. So the parallel hardware here refer to the computer system that are designed to perform multiple tasks simultaneously. Okay, so either through the use of multiple processor or dividing the task among multiple processing units within a single processor. Okay, just like when we're having a parallel executions or perform many tasks at the same time. So here we're talking either we're having multiple processors or we just like dividing those tasks here through or among multiple processing units with a single processor. So this includes systems such as the multi-cores of CPUs or GPUs and specialized hardware like the field programmed gate arrays. Okay, so the parallel hardware is especially useful for tasks that can be easily divided into smaller. Let's say we can divide a specific time the task to independent subtasks that can be executed in parallel, and this commonly seen in machine learning and deep learning, as we know, where tasks such as the training a large neural network can be broken down into smaller tasks that can be executed on different processing units simultaneously, resulting in simplification, speed up, of course, and reduce the time of to train the model. And here, JAX is designed to take advantage of this parallel hardware for efficient computations with features like this function here, this transformation function, Pmap function, that can distribute computations across multiple processing units. Okay, so yeah, this is about the why we need this parallel. And here we're having a snippet of code. The overall of this code, just let's say this code here, we're having a demonstration of how JAX use this Pmap function, and it's how, let's say, it can be used to perform those parallel computations across multiple devices without requiring data transfer. Okay, without requiring to transfer any data between those devices. Okay, so when we talk about parallel hardware, I mean we're having many hardware, let's say one GPU, multiple GPUs, let's say 4 or 5 GPUs. So we don't need to transform some data here through those GPUs or let's say CPUs there. Okay, so this particularly useful for training large neural network where each batch of data can be split across multiple devices for faster training to get a faster result and to save a lot of time during that process. Fine. So let's go to this snippet of code to get deeper in this. First of all, we're importing the random and the pmap function from JAX. Fine. And of course, we will call the numpy function. Of course, always when we're having arrays, matrices, so any of those matrices operations. So here we always call the JAX for numpy. Fine. Here we're writing that create a random 5000 by 6000 matrix, one per GPU. Okay. So we're having parallelly 8 GPUs because we're talking about parallel devices. I mean, we're having multiple devices. Let's say we're having 8 GPUs, and we want to create those matrices here in each one there. Fine. So the first thing, we're creating this key here. We're using this random split, and this is used to generate 8 random keys for each device. Okay, because we have 8 devices, so we will generate 8 random keys. These keys will be used to generate random matrices on each device on those GPUs there. Fine. And here now we're using this pmap function. It's used to apply a function that generates the random matrices also, and those are random matrices for each GPU. Okay, we're applying or we're trying to using random matrices for each of those GPUs that we're having here. And of course, here the resulting matrix are stored in this maths variable, which is an 8. If we want to check the dimension of this maths variable here, so we're having 8 because we're having 8 devices. So it will be A by 50,000 and 6,000. Fine. And now here we're using let's say another pmap function, yes, to perform this dot product between each matrix in this let's say this code here. Okay, and here we're just like applying this dot function on the matrices that we're having and multiply it by the transposite of it. Okay, we're doing the dot between x and xt, which is the x transpose. Okay, with the resulting matrix here, matrices that we got. So we're having the matrix with the shape 8 to say 8 device, and this is the shape of my arrays. My matrix is there. Finally, here this pmap function is used for the third time, okay, to compute the mean of the result that we got here. Okay, we're calculating the mean here. So the resulting array has one element per device, and it's printed in the console using this print function. So we got something similar to this. Okay, so this pmap here just like allow me to calculate the mean for all the 8 devices that we're having at the same time. Okay, and this is the key things about the parallelized function or option for this pmap. Okay, so here we're just like trying to calculate the pmap for 8 devices at the same time. Fine. And yeah, like that, we arrived to the fourth function here, and we said that there are 4 functions for transformations. So the function of transformation, are essential tools for building and training machine learning models in JAX, as they enable efficient computations, automatic differentiation, and parallelization. Fine. So just like to recap everything and to review them again, we're having the grad function to calculate the gradient. Okay, those all those functions, like they are very efficient for doing our neural network. That's why we should have an idea about them. Okay, because here when using neural network with JAX, we will see that there will be some extra coding comparing to the TensorFlow or the PyTorch. So it's good to have those functions in here, those transformation functions in here, and those are the most common used. Okay, the most famous one. We have the gradient that helps to calculate the gradient. We have the dusting time function, just like to accelerate the training, especially in term of time. Okay, and we're having this Vmap function for the multiple inputs. Okay, just like it's applied for a given function to multiple inputs. And we here finally we're having this Pmap to say the let's say to do some parallelizing operation across multiple devices, doing any operation. Like once we're calling this Pmap, and what's coming next here, we can do them across all the devices or many devices that we're having there. Okay, so yes, those are the fourth main transformations function that you should know before digging into the JAX neural network. Hello, hello. Okay, so do you have any question, guys? Yeah, I see that Mr. Atiya is here. Hello, sir. So those are the main things about transformation function. Now let's move to the JAX ecosystem, but we will have just like we won't have some code about it. We just like we'll see together an overview about a JAX ecosystem. But before digging into the JAX ecosystem, before talking about the functions that are mainly there, just let me check what is an ecosystem. Okay, so what do you mean with an ecosystem? So in the context of the software development, an ecosystem refers to a collection of related software tools, libraries, and frameworks. Okay, they are designed to work together to solve a particular set of problems. And we can say that an ecosystem typically includes a variety of tools and technologies, as is mentioned here, that are designed to be used together, allowing developers to build complex systems more quickly and efficiently. Let's say then they could with standalone tools. Fine. So the concept of an ecosystem is often used in the context of an open source software development, where different developers are and organizations of course can contribute to an ecosystem by building and sharing software components that can be used by others. Okay, so here whenever we're talking about ecosystem, always try to link it with the open source. As more components are added to the ecosystem, it's became more robust and powerful, allowing developers to tackle increasingly complex problem with a greater ease. Okay, and if we go to the JAX ecosystem. So in case of the JAX, so the ecosystem includes a variety of libraries and tools that are designed to work together to provide a high performance, easy to use platform for building and training machine learning models. And by leveraging the JAX ecosystem, developers can benefit from the work of others and build powerful machine learning model more quickly and in a very efficient way using those tools, of course. So yeah, this is about the JAX ecosystem. I just like to sum up or the overall things that we were talking about. Just like when we talk about ecosystem, it just like we can use it in the context of the open source. What it's open for all researcher, all developer to add some new things, to add some component, some code to this ecosystem. Like that, it will be more powerful. And same thing for JAX. Also, JAX it's an open source. Let's say it's an open source library that you can add or include in it any new libraries, any additional things that may help the community. So yeah, this is about the an ecosystem and what's JAX ecosystem. Now move to the main tools. Okay, so JAX ecosystem provide a variety of tools for building and training machine learning models, as well as for scientific computing tasks. And we can list here some of the most important tools in JAX ecosystem. So when we talk about JAX in general, we're having the JAX. Okay, you may be wondering why I'm mentioning JAX ecosystem and JAX, because here in JAX we're having some other function. Okay, because JAX is the core library of JAX ecosystem, and it's to provide tools for automatic differentiation, for numerical computations, and for also the GPU acceleration. Okay, we have many, plenty of libraries in this JAX ecosystem. The other thing that we can talk about is the HiQ. So the HiQ here is a neural network library that provides a high-level API for building and training neural network. It's built on top of JAX, of course, because we are always in JAX ecosystem. So it's built on top of this JAX here, and provides a variety of neural network, let's say neural network things, neural network functions, or let's say libraries that or let's say neural-network architecture better, okay, just to include everything, modules or architecture that making easy to build a complex model. Okay, so here if you just like was following between the last session and this session here, so far we what we did in coding part with JAX was only some mathing, some mathematical computations, but we mentioned that we can use JAX to build a neural network. How we can do that? Thanks to one of the tools that is provided in its ecosystem, which is the HiQ. So here, thanks to HiQ, we are able to create a neural network, to design those neural network, to add some layers, to add some weights, and so on. So this is thanks to the HiQ, because Jax alone here can't design the model, can't build neural network. We always need something that help it, which is the HiQ ecosystem, okay, or the HiQ library there. And of course, when we're talking about a neural network, of course, we have some other hyperparameters that may help. We have the optax. So optax here is also is a library for optimizing neural network parameters. It provides a variety of optimization algorithms, such as the stochastic gradient descent. Okay, the same optimizations algorithm that we use to do or to use in TensorFlow. So we're having the stochastic gradient descent, the Adam optimizer, the ADA grade, as well as tools for learning rate, for calculating loss functions, and so on. So here, this HiQ is for the neural network, okay, to build the neural network. The optax, okay, as its name refer here, we're having this opt, so it's you may link it with the optimizer. So the optax function here just like help me to have some optimizer. Let's say it just like help me, or it's provide some optimizers algorithm that's help, or it may be included in the HiQ. So we can build the neural network with HiQ and add some optimizer with this optax. Of course, not only optimizers, but loss functions also. Okay, the only one thing or tricky things be in the optax library here, just like we are obliged to specify a specific learning rates. Okay, we should, for example, if I'm using the Adam optimizer using this optax here, I'm obliged to add a learning rate there. Okay, so as you know, in TensorFlow sometimes we don't specify those details in specific optimizer, but here in optax we can, we'll talk about the optimizer part. We should have some learning rate there. And also the variety of loss functions, let's say the L1, the L2, we have plenty of loss functions that may be provided by this optax function. Fine. Now the other tool is the LLAX. Okay, LLAX is a library for reinforcement learning. Of course, always the first letter here just like help me to have an insight about what this function does. So here, this LLAX here, just like it's help for the reinforcement learning, as I mentioned, all the reinforcement learning tasks, and it provides tool for building and training reinforcement learning model, as well as a variety of algorithm and environment, of course. And here we're having NumPy, the popular NumPy. And who don't know NumPy? Of course, if you are attending the session, so for sure you'll know the NumPy, which is the Python library. And JAX provides a drop-in replacement for the NumPy that optimized for GPU acceleration and provide the automatic differentiation. So we're having JAX for NumPy, and we can consider it as one of tools that is included in the JAX ecosystem, the huge JAX ecosystem. That was about the NumPy. Moving to the Flax. So Flax is similar to the HiQ. We can say it's not similar to HiQ, but both of them are used for neural network. So we can say that Flax is a neural network library that is built on top of JAX, of course, and provide a higher level APIs for building and training neural network models or more neural network in general. And also provide tools for distributed training, making it easy to scale to training multiple GPUs or even multiple machine at the same time. Fine. And here we're having this HiQ for Torch. Okay, you may guess it based on the name. So the HiQ to Torch is a tool for converting HiQ models to PyTorch, allowing users to take advantage of the PyTorch ecosystem for training and for a deployment. Of course, we've included this HiQ, so we can do some task here with the HiQ and convert those models into the PyTorch. So we will let's say pick the advantage for both ecosystems, for both libraries or for both framework here, the HiQ and the PyTorch. And of course, we're having something else, which is the Optuna. So it's a hyperparameter optimization library that can be used with JAX to find the best hyperparameter for a given function, for any specific function. Of course, there are plenty of other things. Those are the main used one or the main famous one. Just like, do you have any question, guys? Any question, guys, related to JAX? So just like to, if you want to sum up, the JAX ecosystem provides a wide variety of tools for building and training machine learning model, as well as for a scientific computing task. The tools are designed for to be flexible and to be efficient, and also it's tried to make the experiment very easy with the different models and different techniques, and also it's scale up training to large data set and the compute clusters. And as always, I mentioned in the last session, deep learning is just like a very tiny part of what really JAX do. Okay, so JAX is very huge. It's a very computational library or framework, and deep learning is just like a small part of it. So, and those tools here just like help the JAX to do a lot of computational things, as well as training some neural network and training some machine learning models. Okay, so yeah, that's it about today's session. Do you have any question, guys? Any question, guys? Okay, we can wait for some couple of minutes, let's say for 5 minutes or things. Thank you, Atiyah, for attending. Really got to see you here again. Thank you. Okay, so in the next session, inshallah, we will try to see some codes related to the JAX ecosystem. Okay, so all those tools that we mentioned today, especially for those related to the neural network, like the HiQ, the Optax neural network, we will try to write some codes to explore those JAX ecosystems and to know how to build those neural networks using JAX. Okay, away from TensorFlow, away from this easy thing that we have, that's been more efficient way and in more sophisticated thing. Okay, and of course, if you want to know more about my work, you can just like follow my GitHub repository here under the Leila 828. Fine. So if you don't have any question, thank you so much for attending, and see you in the next episode, inshallah. Salam. Bye bye.